Test. 1, 2, 3. Is that my condenser mic, though? That's the question. That's this one. Test. Test. Okay, that should be good. Gotcha. Well, it wouldn't be a Dr. Moore stream if I didn't start off with the friggin' mic muted, wouldn't it? Ha! Well, anyway. So anyway, ugh. I started feeling ill Friday evening after I got home from work. We actually went out for Indian food. And then by 10 or 11 at night, I was, perhaps re-encountering food previously encountered, let's say. And that was a state of affairs which persisted the entire night. Somehow I still got a better night's sleep than my wife, though, who's, quite heavily pregnant. And, so, like, Saturday was kind of just a write-off. I apologize for missing the makeup session. I think we're going to have to hold it this coming Saturday. At this point, it's kind of the cursed lecture. We'll see what I catch for next Saturday. But, yeah. So thank you for your well wishes. I'm feeling much better at the moment. Back to eating food again, and all that kind of stuff. But I did develop a bit of a cough yesterday, which fortunately seems to have abated. And I'm, I just don't want to spread it around because, like, you don't want what I had, basically. But yeah, I think actually the cough that I had developed was just like acid damage to the inside of my throat from all of the all of that stuff. So yeah, I kind of got like soreness in my like lower rib cage, which I think is attributable to the same explanation. It was just a really intense bout of tossing one's cookies. It was terrible. But yeah, anyway, how's everybody doing today? Now that I've wasted the customary first 3 minutes of the lecture while people arrive, eh? This should give some idea of the latency as well. I think maybe 50 concurrent viewers is as much as we can hope for. 53. Not too bad. Okay. Well, I realize that even for a Monday morning stream where you don't technically actually have to be in the room, it's still pretty early in the morning relative to an undergraduate anyway. Anybody in the room? That would be interesting to know. Anybody go to the room anyway? I can give you the projector code so you can put me up on the screen if you want. Oh, wait. No, you can't. On that one, you have to log in using your Mac ID. But in theory, I don't know. I guess anybody with a Mac ID can get into the projector there. You just have to log in and open up that stupid software. But, so about 1/4 of the people went to the lecture anyway. There you go. So, Might as well get into it. Let me just check the announcements feed, see if there's anything pertinent in there, aside from all of the stuff that I've been talking about previously. Oh, maybe I didn't say we got a new TA. Maybe I did. Celine is now joining us. She seems to be very on top of her game, so I'm happy to have her on the team. I was trying to connect my laptop to the HDMI, but I couldn't figure it out. So all you have to do, right? All you have to do is just load the YouTube video up on the Podium computer, and then you don't have to worry about it. But, yeah, you have to... There's like a green icon on the desktop that is like the AV control center. Double click on that and then click laptop input, and then the HDMI cable will work. So, yeah. At any rate, so we were just talking last time about big O notation. We got a little bit into it. We were talking about timing functions, how one might go about deriving a timing function should one have the need to do so, and, you know, primarily what we're concerned with here is the, like, we should have a fairly firm concept now of what, like, how a timing function is constructed. Now we're going to talk about the various approximations that are made that refine our timing functions back down into, excuse me, something useful for sort of immediate and intuitive comparison. Whether you think this is intuitive, of course, is best left to the imagination. But we were talking about our bubble sorting, this bubble sort procedure. Hopefully most of you have seen bubble sort at one point or another. I'm pretty sure anybody who took C programming with me had to do an implementation of bubble sort in C. So you should know it that way. So essentially, with bubble sort, all of the stuff in the middle, in the most high level loop, the most nested loop, everything in this sort of region, all of these lines are collected up and multiplied by n squared, which is the number of times this loop is executed, with an asterisk hanging off the end of that we're going to talk about. Then anything inside of this loop, which as it turns out at the moment is just the evaluation of this for expression, gets multiplied by n, and then of course we have CF for, you know, the function call overhead. This is getting very difficult already. We may notice that when you're having something like, you know, 3 constants added together, it's just as easy to say, oh, well, let's just name another constant for that, slap that on, and then we don't have that long, complicated expression filled with constants. While you do lose a certain amount of detail in this approximation, the detail isn't interesting or pertinent to what we're trying to establish, right? What we are trying to establish is the relationship, the rough relationship between the growth in the magnitude of the things we're processing and the growth of the runtime of the algorithm itself. So, essentially, we can simplify our expression by setting some new constants equal to the values of other constants. So there we go. So this kind of breaks it down into what you might think of as a typical second-order polynomial expression, of the sort that you should be well familiar with from your careers in high school algebra. So let's think about this now, right? Because we're thinking about how quickly this function grows as n increases, right? So I've got this nice little chart here which gives you the percent contribution to the total value that this function evaluates to as n increases, right? So this is assuming that we're setting all of these constants to 1 for the sake of argument. This is probably not a fantastic, this is not meant to be representative of, the algorithm itself, but it is meant to show you that, if you just had n squared plus n plus 1, over time, which one of those terms comes to dominate, right? So you can see that our constant term, 1, while all of these terms are contributing about a third of the exactly a third of the total value at n is equal to 1, as n increases, the constant drops off pretty precipitously, and, by 15, you can barely notice the effect of it at all. N takes a bit longer, but, you can imagine this extending off to, like, say, 500. By 500, basically the entirety, almost the entire thing is being contributed by the n squared term. So there's a very, very important concept that's, like, pivotal to understanding big O notation. And that is that over time, as n grows, the contribution to this equation by constant terms falls away and becomes almost meaningless. So, and this is irrespective of how large that term is, right? So this is like a kind of this is like a convoluted, high-minded mathematical point. So I'm sure all of you people in the COMPSCI and mathematics program will get this very quickly. But it basically works like this. If you have a term, like, say, a times n squared, it doesn't matter what a you choose, right? Whatever a you choose for this constant, so long as it's finite, right? So long as a is finite, n squared can always be made much, much larger than it, right? Because all you do is you just pick some, like, let's say you set n equal initially, like, to the root of a, so that you have essentially a times a, so a squared being the total value of this term, right? Well, n it's a function on n, so n is going to increase from there, right? So as n increases, the a term is going to dwindle away down to almost no contribution relative to the contribution of the n squared term, because this guy is going off to infinity, right? Another way of thinking about this is like thinking about the limit as n approaches infinity, right? Which of these terms is going to be the most dominant, right? You guys with me so far? Let me do one of my famous "you with me so far" polls. So, this is kind of key to understanding what's going on with big O, right? Ah, good. So this leads us into the idea of a tilde approximation. So we write tilde f of n to represent any function for which the limit as n approaches infinity of tilde f of n over f of n is equal to 1, right? So if you remember your limits from, calculus, the way that you take a limit, right, is you're only concerned with the highest power, and these powers will cancel each other out if they're, above, and if you have n to the fourth down here and n to the fifth up here, then that comes out as n, just n. That goes to infinity, so you end up with infinity on the top, right? Similarly, if you end up with an infinity on the bottom, that goes to 0. But essentially, you only have the limit of that ratio coming to 1 if, well, you need two conditions. The first condition is that the powers, the sort of strength of the highest power is the same. And number two, the constants need to be the same as well. So, applying this to the equations that we've previously derived, and dropping everything but the highest, this drops everything but the highest order term. So, if we have f of n being this series of constants, then tilde f of n will need to be the same series of constants. If we have f of n c2 plus c3 times n plus this other constant, then tilde f of n will be that same c2 plus c3 times n, but we drop this part. And if we have our equation for bubble sort, c3 plus c4 plus c5 n squared plus the rest of it, you'll see that tilde f of n is just the highest powered term, right? So, if you're not that good at calculus, you can sort of run a reasonable approximation of this procedure in your head by just writing down on your cheat sheet, tilde approximation means take the highest power and its constant term. All right? So, further observations and simplifications. We might also observe that as n grows, the effect of the given constant is proportionally reduced. This is what I was banging on about a few slides ago. This leads to a so-called order of growth approximation. The O in big O stands for order of growth. Essentially, we are taking a tilde approximation and also dropping the constant on that tilde approximation. Notationally, we take this approximation x and write it as big O of x, which is pronounced big O. So, if we have these if we have our time function for the swap operation, our tilde approximation of that does not change much. But our big O is big O1, or big O of n to the power of 0, right? You have to imagine like a little n to the power of 0 hanging off the end of that, right? Anything to the power of 0, of course, is 1, so, and 1 is a constant, so we call this constant time, right? With respect to our linear search algorithm, our tilde approximation was c2 plus c3 times n. Our big O order of growth approximation of that is big O of n. And of course, for bubble sort becomes big O of n squared, because that's the highest ordered term. Any questions? Boom. I want to actually, while people are entering questions, if they have them, return to the bubble sort algorithm, because I had a question at the end of class last time, which I think is highly pertinent and interesting. So, and this sort of answers questions in general about if statements as well. Can you please explain again why constant time algorithm has to be big O1? Why is it always 1? So it's very simple. We want to drop all constants, right? So if you had an equation, have we talked about the first one page? Yeah, the previous bit we covered in lecture last time. There should be a video on my YouTube channel, so feel free to watch that. So let's imagine that we had like some other big O thing, right? Let's say we had big O of 7, right? We can rewrite that as big O of 7 times n, and I really wish I had my chalkboard. Sorry. Big O of 7 times n to the power of 0, right? Since big O always gobbles up constant terms, we are left with merely, what am I doing? Big O of n to the power of 0, right? Which, of course, anything to the power of 0 is 1. So it doesn't, like, that's the reason that 1 is always used. It's because anything else is considered a constant that you would drop. Make sense? Good. Hopefully, anyway. So I'm going to have to open up a... I actually do need something approximating a chalkboard, so I'm going to open up my favorite Linux-based image editing program. If you are a Linux user and you are not using Krita, then you are a fool. A fool, I say. And I say it unapologetically. GIMP is for wimps. Ha! I said it. That's a bit too thin. That'll do. We'll do it in black. There we go. All right. So I'd like to return to bubble sort here, because this is a good illustration of one of the general principles here. So you may notice here we have based our timing function on the assumption that both of these loops will execute n times. This is not actually the case if you read the algorithm as written, right? It is the case for the outer loop. We go from we go from 1 to a dot length minus 1. We'll just, absorb that other like -1 issue, This is like an indexing thing, right? But if we take a look at the second loop, we've got for j from a dot length down to a plus 1. So we're actually counting down in the case of this inner loop. But you'll notice that we do not count from the top, that we're not counting the full width of n. In fact, every time n steps up, this bit gets a little bit shorter, right? So I'd like to visualize that for you, right? So if we imagine if we have, you know what? I'm going to use painting tools. Let's imagine we have n squared. The gas fitter is here. Don't worry about it. It's not your concern. So we have n squared, right? This would be the runtime if we had both loops executing the full amount of n. You can imagine like a bunch of little squares in here, each one representing one iteration of the loop, right? Geometric analogy. So if we took the bubble sort algorithm as written, what we actually have is something that looks more like that, right? We have, in fact, a triangle, right? Because each time n increases this way, the number of iterations get a little bit shorter this way, right? So what's the area of this triangle? Anybody? Assuming everything's perfect and the way that I've drawn it. Somebody in the chat, shout it out. What's the area of this triangle? Half of square. Yes. Yeah. So it's n squared over 2. Right? So this, that is, you know, if we were to take it into math land, right? N squared over 2 is equal to 1 over, like, you know, 0.5 times n squared equals big O n squared. So essentially, even if these, even if you're not actually fully executing the loop, the area, so to speak, using the geometric analogy, the area here is still proportional to n squared, right? It's just a matter of modifying the constant term. So even if you drop half of this, it's still, the order of its growth is still proportional to n squared. So it's still big O n squared, right? And this also applies to basically any if statement inside of a loop that you know is going to execute, that might execute more than once. Like some if statements inside of loops will only execute once because they've got like a return statement or a break statement inside of them. But you even have to be careful with that. A break statement doesn't necessarily mean that that statement will only be executed once, because it might be, you know, how many loops are you breaking from, right? With a break statement, only one. So if it's like a triple nested loop and you are only breaking once, then you could do that like still n squared times, right? So it really just pops it down to the next lower level. But anyway, a return statement, though, that kills the algorithm directly. So you only get to execute one return statement in the whole thing. But yeah. So yeah, despite the fact that we're not actually fully executing any of these loops, we are still in big O n squared land. Does that make sense? So these types of geometric analogies are very useful when you're, you know, trying to reason through how big O works. Cool. So, good. So, big O notation in general provides us with a much-needed classification scheme for categorizing algorithm behavior. When an algorithm is described as logarithmic, exponential, linear, etc., we are describing what function the algorithm's growth is proportional to. So you'll notice that in this class I've already been using that type of terminology quite a bit, and if you were paying attention back in 1MD3, and if you were, you know, if you took 1XC3, with any time you've had me as a prof, you've likely heard me use these terms. You've likely heard other profs use these terms. Now you should have a good, firm, solid understanding, at least from an intuitive perspective, what big O actually means. We're going to have a somewhat more formal definition in like one more, maybe two more slides. I forget if there's a comic there. Probably there is. So now you should have a fairly firm, intuitive understanding of what big O means, right? So this is, you know, we have various These are a number of big O functions with their descriptive words in order of goodness. So constant time algorithms are always preferred to everything else, unless you have to buy them at the price of, really bad algorithms elsewhere. Logarithmic is normally the best you can hope for. Linear is good enough for most situations. Linearithmic is, still pretty good, but, not as good as the other ones. Quadratic, we're starting to get into, well, this could start to take some time territory. Cubic is like, okay. Exponential, avoid like the plague. Unless you are obligated by just the mathematics of the situation to need an exponential algorithm, which is often the case when dealing with NP-complete problems. In fact, that's what NP means. I don't have a slide on this, but NP means non-polynomial, which means that the order of, basically that's a reference to the big O notation for that algorithm. It means that we don't have a polynomial time algorithm to compute it, which means that we are in exponential territory, or possibly even factorial territory, which is terrible. So you can see, this is just an interesting little aside. This, by the way, is the traveling salesman problem, which is a, it's an extremely well-known, terrible problem, NP-complete problem. The brute force solution to the traveling salesman problem is big O n factorial. And of course, with better algorithms, we get it to n squared 2 to the n, which is better than factorial, but still terrible. And then selling on eBay is, of course, you don't have to travel at all. So that's the joke. But essentially, the traveling salesman problem, like a rough description of it, given a graph given a network with a bunch of nodes and distances between those nodes, what route can you take? What's the shortest route between all of the nodes in this graph that connects all the nodes in this graph? I think without retracing, but so you go. Yeah. Dynamic programming is something we might talk about a little bit towards the end of the course, but I know I covered it fairly extensively when I did the grad level version of this course. So it's kind of funny. I did the grad level version of this course, but I never did the undergraduate level of this course. So I've got like, I'm going to be learning hash tables along with you guys, basically. Question. Good question. So the power of n only increases when loops are nested, correct? Correct. That's an important point, yeah. Because, see, the thing is, right? Let's say you had 2 loops, right? So while, let's say for I in L, and then later, and I would do this in Python just because, for J in L, right? These guys would contribute some constant, call it x, times the length of n, or the length of L, which I'll call n, plus the runtime of, y, let's call that ASDF2 times n, right? Collect the terms, call it a constant, you're off to the races, right? If they're sequential, they only increase the value of the constant. Since we're not fundamentally caring too much about the constant, that's, that doesn't affect the big O categorization. Now, I shouldn't be too flippant about constants, because a great deal of very important optimization occurs because, inside of those constants. A great deal of a great deal of scientific research is in getting those constants down. But, we're learning the basics here. We want to know how to categorize algorithms. How could we get n to the power of 1? Root n? So, there are some things I'm not telling you. You might also ask how one gets to exponentiation, right? Or how one gets to logarithm. Basically, right now, I've only explained how we get to the polynomials, right? We'll kind of, get there when we get there. This is good enough for now. But, the answer is recursion. So, yeah, the power of n can also increase in some cases of recursion as well. Yes. So, you guys remember for 1MD3 when I did the Fibonacci example, right? You guys, oh man, I'm missing my blackboard. You remember how, to calculate recursive Fibonacci, we needed, to calculate 4, you had to calculate 3 and 2. And to calculate 3, you needed 2 and 1. You remember this? I didn't show you this for no reason. Right? Because everything's got the only base cases are 1 and 0, right? Now, this is, in this case, we're going on, the raw numerical size of the input to the function, rather than the number of inputs in the number of elements in a data structure, which incidentally makes this a super bad algorithm. But, because, for every, how might I want to say this? You have to, the maximum depth of this recursive call is the number that this number is, right? That's the maximum depth of this tree. But the breadth of the tree is, it's not quite, 2 to the power of this number, but it's proportional to 2 to the power of this number in the same way that this guy is proportional to n squared, right? Since each node in this tree has to be processed by a recursive call to the same algorithm, that means that this bad boy is big O n to, big O 2 to the power of n, right? We're going to see other algorithms like binary search, when we talk about it, that basically flip this on its head and require only the log of the number of input, log base 2 of the number of inputs to find its answer. And those are logarithmic algorithms. So it really depends on the structure of the algorithm, but once we start getting into fancy stuff, we're going to start talking about recursion a lot more. How will memoization change the fib algorithm from to the power of n to more efficient algorithm? Well, in the case of this guy, because these guys start being able to remember it, basically you just travel down one side, and anytime a number is called for, you just do a ideally constant time lookup in in a linear data structure, which reduces, it means you don't have to do all of these recursive calls, which turns that with memoization into a linear time algorithm, again, on the number here, not the number of numbers you're inputting, which is always, just 1 in this case. So there you go. Of course, the cost that you pay is you're now going from requiring constant memory to linear memory, But, you know, it's a good trade-off. Anytime you can avoid an exponential function, it's a good trade-off. So, let's talk about big O a little more formally. Incidentally, I know that we're like a little bit behind with respect to the sort of order of things that were previously prescribed, but like I feel with these courses it's really, really like this intro material, what's considered intro material here, I don't think is actually intro material. It's like you have to get this. This is not optional material, and I don't want to like sort of glance through it too quickly because I want you guys to really understand what's going on here, because this is fundamental to your entire the entire rest of the course and the entire rest of your degree program. Like big O is really important. So, yeah. Anyway, so formally, big O of some function f of n denotes a set of functions. So we, you know, where previously I wrote things like, you know, equals sign here, what I should actually be writing is the set notation in thing here. So quick question. This isn't really related to the lecture, but for the tutorial questions, are we expected to do those before the tutorial or work through them with the TAs? So for this week's tutorial, I have elected that you will actually do some Java programming. So if you... Oop, pardon me for a second, folks. It would be useful for you to already have the Java runtime, the Java Standard Development Kit installed. Instructions are on the tutorial sheet, so that'll give you more time in class. But no, my expectation is that you work through the problems in class with the TA and all the rest of your colleagues, collaborating in the way that normally is not allowed on assignments because it's academic dishonesty. Yeah, it's like collaboratively develop the solutions, and so you all understand what's going on, please. If you have questions, ask people, and then get answers to those questions. No, you're not expected to have all the answers before you get there, because then why would you need an hour for it? That said, I did assign like way more programming than I think is reasonable for you to get done in tutorial 2 and said, the rest is homework, so, you know. But anyway, so if we have some function f of n, which might be squared, might be 2 to the power of n, big O of that denotes a set of functions. Membership in this set is determined by the following. Given the existence of some constant c and some number of inputs n naught, for all n greater than or equal to n naught, if the timing function is between 0 and f of n, that's the f of n described by big O, multiplied by the constant, then then the timing function is in the set denoted by big O f of n. So, you have some function, f of n, you multiply it by an arbitrary constant, right? So, the point is, this constant can be anything you like. It just can't grow, right? It's not a function on n. So, like in the same way that like the constant eventually becomes meaningless when we're taking big O, right? This is like kind of the scientific explanation for that. It's like t of n needs to be bounded by this constant term times f of n, right? So t of n always needs to be between these two, between this guy and 0, right? Now, this business with n naught basically just means, as you know, there might be some like earlier kerfluffery where this is not true. So long as this is the case, like going off to infinity, that's what we're concerned about, right? This is the main issue, right? We're concerned with the behavior as n approaches infinity. So if there's like, even if it's like, you know, this property doesn't hold up to n is equal to 10 million, so long as it holds, you know, for all time, basically, after n is equal to 10 million, then it's still bounded in the uppercase by this function, right? So effectively, big O f of n is an upper bound of t of n past some arbitrarily selected n naught. If we were to put that in math speak, there exists some c greater than 0 such that there exists some n naught greater than or equal to 0 such that for all n greater than or equal to n naught, 0 is less than or equal to Tn is less than or equal to c times f of n, states that t of n is an element of big O f of n. So this has some interesting consequences. Let's consider the timing function t 32n squared plus 17n plus 1. Which of the following are true? In other words, can we select a c and an n naught such that any of these are true? So, is t of n an element of big O of 1? How about n? How about n log n? How about n squared? How about n cubed? How about n 2 to the power of n? Which of these statements are true? Enter your comments now. Oh, does Python list index lookup take big O of n? Because isn't it implemented by linked lists in C? Yes, I would think so, actually. I would think so. Only the last three are true? Let's see if some other people have some comments there. The last three? The last three are true. You're correct. For those of you who were following along in the slides and looked ahead, shame on you. So, t of n is not an element of big O of n. It's not an upper bound, but all of these last three are upper bounds. However, this is not necessarily useful information, right? In general, we want our bounds to be as tight as possible. While it is technically the case that big O 2 to the power of n is an upper bound for, 32n squared plus 17n plus 1, that does not convey as much useful information as big O n squared, right? Because this forms an upper bound to pretty much everything, right? Just like big O of 1 forms a lower bound to just about everything, right? So really, you want your information to be as informative as possible and to select a function here which binds as tightly to the function you're describing, or to the algorithm you're describing, as possible. It's like Price is Right rules, except in this case, it's as close as possible without going under. So, I guess we'll hold that for the rest. We'll hold that for the next time. Any questions? If there are no questions, we'll wrap this baby up. You guys feel like you're learning things? Hopefully this isn't all stuff that you'd already known. Hopefully this illuminates things for people. I'm thinking, you may have, come across this type of material in, 1JC3 or something, but, for those of you who are, doing minors and that sort of thing, you may not have ever seen this before. So, and if you're doing a minor in computer science and you don't know what big O of n is, or if you don't know what big O notation means, then, you know, we will have failed you as an institution. Cool. All right, well, I guess I'll sign off here. Thank you very much for your time and attention today, folks, and see you on Wednesday. Oh, yes. Unless otherwise informed, Wednesday's class will be in person. So this is like the worst case scenarios. Yes! Very much so. Very much so, Timothy. Big O notation ordinarily denotes the worst case scenario, or the upper bound of the runtime. Next time in class, we'll be talking about big omega, which is the lower bound, or best case scenario, and big theta, which is the, I guess you could say both. It's when one function is both the upper and the lower bound, then it's big theta. Take her easy, folks.